Welcome back to Precalculus, everybody. Today we start chapter 4. We're in section 1 talking about inverse functions. Okay, so the first thing we need to understand about inverse functions is some vocab about it. It's particularly if it's one-to-one. Okay, so a function is one-to-one if every element in the range corresponds to exactly, you might want to underline exactly again, exactly one element in the domain. Okay, so the test that we use to determine this is the horizontal line test. Okay, it is a visual test to determine if a function is one-to-one. So we're going to take a look at that here in the next few examples, whether these functions are one-to-one. So if we take a look at this first example, and you can ignore the B's and G's, again, that's just some printer code error. But let's look at this. Let's run a horizontal line through it. Okay, I'll just draw a horizontal line through it. You can see that this hits the function twice. Okay, that means that each element of the range, this one which here happens to be the number 3, corresponds to more than one element of the domain here and here. Okay, so this is not one-to-one. Okay, this next one we can run a horizontal line through anywhere we want, and we're only going to hit the function one time. So it is one-to-one. Okay, and lastly, this function right here, we run a horizontal line through somewhere in the middle there. We're going to hit it more than once. So it is not one-to-one. The horizontal line test is very similar to the vertical line test, except we're using horizontal lines. Okay, so now let's talk a little bit more about inverses. So if f is a one-to-one function, one-to-one function with some ordered pair, okay, we can call it whatever we want, a, b, then we know that the inverse, which is denoted f negative 1 of x, is a one-to-one function with ordered pair BA. Okay, and we can even erase this one-to-one. We can just say we know that the inverse is a, let's just call it a function. Because when you inverse something, you're going to see when you inverse the horizontal line test, you're going to get the vertical line test here in a minute. Okay, so the range of f happens to be the domain, oops, sorry, I wrote it in the wrong space. It's the domain of the inverse. Okay, and you can see that there's b is the y coordinate, now b is the x coordinate. And it also happens with the domain. So the domain of f is the range of the inverse. And you can see that a is the domain of f. It is now the y coordinate or the range of the inverse. Okay, so if we want to have a little diagram about how the inverses work, so imagine we have a set here. We'll call this the domain, or the x coordinate. A function takes elements of the domain, a function f takes elements of the domain and maps them to elements of the range, or y coordinates. An inverse essentially undoes that. Okay, so an inverse takes elements of the function's range and maps them back to the function's domain. Pretty simple to understand. So let's take a quick look at an example here. Okay, I'm going to rewrite the function because it's hard to read with all those b's and g's in there. But what it says is x plus 2 quantity cubed minus 1. And if we look through, we just want to find some points in this function. It's graphed for us. It's clearly a cubic S-shaped graph. Let's find some functions of f. There's some points on f. So I see I got a point 0, 7. I've got a point negative 1, 0. a really easy point, -2, -1. I see I've got a -3, -2, and a -4, -9. Well, now that we have all those xy coordinates, I know that to find the inverse, all I have to do is flip those xy coordinates. So now 0, 7 becomes 7, 0. The next point will be 0, -1. All I'm doing is flipping the x and y. The domain and range are flipping. So -2, -1 becomes -1, -2. Next one will be -2, -3. And then -9, -4. Okay, so graphing this, not too difficult. -9, -4 is about right there. Got my 3 points there. And I've got 7, 0 right there. And I can see, try to draw as smooth as possible. There's my inverse I drew in pencil. And if we look closely, we can see that this is a perfect reflection over the line y equals x, okay? Which should make even more sense to you because in our original function to our inverse function, the y coordinate becomes the x and the x coordinate becomes the y. Okay, so now let's talk a little bit about finding the inverse algebraically. So a few steps we need to consider, and this will be kind of second nature by the time we do one example. But we want to first start off by using y instead of f of x. That's going to make life a little easier. We're going to then interchange the x and y variables. Okay, an inverse is a reflection of the line y equals x. Should make sense. Flip the x and y. We're going to then solve for y, and we're going to substitute f to the -1 of x back in for y when we're done, just so we have the correct notation. So let's take a look here at this first one. It's the one we just did on the front. So it's going to be y equals the quantity x plus 2 cubed minus 1. So that's the original function. To find the inverse, we are going to flip them. So this is going to change into x equals y plus 2 quantity cubed minus 1. And then we have to solve for this y. Okay, so let's just start solving. So let's start off by adding 1 over to the other side. So we got x plus 1 equals the quantity y plus 2 cubed. And then to get rid of a cube, we got a cube root. So cube root of x plus 1 equals y plus 2. Running out of space, so I'll go up here. And the last thing we have to do to solve for y is just subtract that 2 over. So y equals the cube root of x plus 1 minus 2. Okay, so this is our inverse. We can rewrite it with the inverse notation. It says the same thing, cube root of x plus 1 minus 2. And you can notice now that, look, a shift to the left 2 in the original function becomes a shift down 2 in the inverse. Again, there's an example of the x and y trading places. And look, a shift down 1 is going to become a shift left 1 in the inverse. So what I want you guys to do right now is take this function f of x equals 2x plus 1 over 3x minus 2 and see if you can switch the x and y, solve for y, and find the inverse algebraically. Okay, I will just do a quick reminder that to solve, you're going to want to multiply by a denominator at some point, and you're going to need to factor something out at some point. So give it a shot, see if you can find the inverse algebraically of this function. Okay, the last thing we're going to do is we're going to verify that two things are inverses. So to verify that f of x and f inverse of x, even though it seems logical, the way it's written, that they are inverses of each other, meaning that one is sending the domain back to the range of the other. Then that must mean that f of f inverse of x is equal to x, and f inverse of f of x must equal x. So So if you look at those two definitions, like look at this one, if you plug x into a function, you'll get out a y value, and then you take that overall value, plug it into your inverse, and you get out an x. Should make sense. Okay, so we're going to verify that our original function that we've been playing with all day today is its inverse. Okay, up here. Sorry. We're going to verify that this is the inverse of this. Okay, so let's try it out. We're just going to take the inverse and plug it into the original function wherever we see an x. So the original function said the parentheses, now it's quantity x plus 2 cubed, so we're going to have to plug in that inverse, which is cube root of x plus 1 minus 2 plus 2 cubed minus 1. So let's take a look and see what happens here. Well, the minus 2's and plus 2's are going to be gonzo. So now we've got the cube root of x plus 1 cubed minus 1. The cube and the cube root are going to cancel out. Leaves us with x plus 1 minus 1, which obviously those cancel out and leave us with equal to x. So when we plug the inverse into the original function, we simplified and got x. Now we have to do it the other way. So let's take the original function and plug it into the inverse. Okay, so the inverse was cube root of, and then we had an x. So we got to plug in x plus 2 cubed minus 1. And then we had a plus 1, and then minus 2. So the minus 1 plus 1 underneath, those cancel out. Quantity x plus 2 cubed, cube rooted, minus 2. The cube and the cube root are going to cancel out. Leaves us with x plus 2 minus 2, which simplifies to x again. So if they both simplify to x, then that means that they are both inverses of each other. If they, for some reason, one of them does not, then that means they are not inverses of each other. Okay? Just a quick note, when verifying inverses, it is not simply enough to just switch the x and y and solve. Here, you're algebraically finding the inverse. Down here, you are algebraically verifying that the two functions are inverses of each other. Thanks, and I look forward to helping you guys in class.